Welcome, stargazer. Tonight, we journey through our cosmic home, the Milky Way galaxy, that luminous river of stars stretching across the night sky. Let your body sink into comfort. Let your breath slow and deepen. There's no destination tonight, no urgency, just gentle wonder as we drift through our galactic neighborhood, discovering the magnificent structure that cradles our entire existence. If you find peace in this journey, consider leaving a like and subscribe to explore more cosmic mysteries with us as you fall asleep. We have endless wonders waiting among the stars. You live inside a galaxy, not near it, not orbiting around it, but inside it, embedded within a vast spiral of stars, gas, and dust stretching across 100,000 light-years of space. Every star you've ever seen with your naked eye belongs to this one galaxy, our Milky Way. You're not looking at the galaxy from outside, but experiencing it from within. Like a single cell, aware it's part of a body, a drop of water, conscious of the ocean. Let's begin our gentle drift through this river of light. The Milky Way contains between 100 and 400 billion stars. That's more stars than all the grains of sand on all the beaches of Earth. Yet they're spread so far apart that most of space remains empty, dark, silent. If you could hold the entire galaxy in your hands, most of what you'd grip would be vacuum stars, separated by distances so vast that light takes years to cross between them. Yet these sparse points of light create structure, beauty, the spiraling magnificence visible on clear, dark nights. Imagine every human who ever lived, about 100 billion people across all history, each one representing a star that barely reaches the low estimate for our galaxy's stellar population. The Milky Way could contain 4 times that many stars, 400 billion suns, each potentially hosting planets, some perhaps harboring life, intelligence, civilizations, wondering as you wonder now about their place in the cosmic vastness. This immense population creates the soft glow you see on dark nights. The Milky Way's band, stretching across the sky, isn't fog or clouds, but countless distant stars, so many that they blur together into continuous light. Like city lights viewed from an airplane, individual sources merging into luminous streams. You're seeing your galaxy from inside, looking through the disk toward the crowded galactic center, where stars pack more densely than anywhere else nearby. Each of those stars is a sun, some larger than ours, some smaller, some younger, some older, some already dead, though their light still travels toward us. They're distant siblings, born from the same primordial nebula billions of years ago. Family members, separated by incomprehensible distances, yet bound by shared origin and mutual gravitational embrace. You're made from their substance. The atoms comprising your body were forged inside stars that lived and died before the sun formed, their material scattered through space by supernova explosions, later gathering into new stars and planets. Your star stuff, literally. Cosmic material recycled and rearranged into temporary form, capable of contemplating its own stellar origins. The Milky Way is a barred spiral galaxy. It has a central bar-shaped structure of stars, about 27,000 light-years, long, roughly 1/4 the galaxy's diameter, with spiral arms extending outward from the bar's ends. This bar rotates like a solid object, stars moving together through the galactic center, creating the backbone from which our galaxy's spiral structure flows like water from a spinning sprinkler. Our solar system orbits far from this central bar, We're located in a minor spiral arm called the Orion Arm, or local spur, about 26,000 light-years from the galactic center, roughly halfway out from center to edge. It's a quiet neighborhood, away from the crowded, chaotic center, in a region where star formation proceeds gently, where space between stars is vast enough for planetary systems to evolve undisturbed for billions of years. This location might not be coincidence. The galactic habitable zone regions, where life can most easily arise, might lie in these outer regions, away from the radiation-intense core, away from the frequent supernova of spiral arms, in relatively peaceful orbital zones, where evolution can proceed without constant cosmic catastrophe interrupting. We orbit the galaxy at 828,000 kilometers per hour. That's 230 kilometers per second, more than 500,000 miles per hour speeds beyond human comprehension. Yet you feel nothing. Earth, Sun, solar system, and local stars all move together through space, like passengers on a cosmic train, velocities so perfectly matched that relative motion is imperceptible. You're hurtling through space right now at ridiculous speed, yet you rest peacefully, unaware of the motion. The Sun takes 225 to 250 million years to complete one galactic orbit. Astronomers call this time span a galactic year or cosmic year, the time required for our solar system to circuit the Milky Way's center once. Since the Sun formed 4.6 billion years ago, it has completed only 18 to 20 galactic orbits. Earth is young by this measure, only 20 cosmic years old, still in its galactic childhood. Dinosaurs roamed Earth less than one galactic year ago, when Tyrannosaurus rex stalked prehistoric forests 66 million years ago. The solar system was nearly in the same galactic position it occupies today, having moved only about 1/4 of the way around the galaxy since then. In galactic terms, dinosaurs are recent, their extinction a contemporary event, humanity's entire existence a mere moment. This perspective makes human concerns seem appropriately small. Your worries, your struggles, your triumphs all occur within a time span the galaxy barely registers, on a planet that's completed less than one orbit around the galactic center since complex life emerged. Yet this smallness isn't diminishing but liberating, placing your existence within context so vast it makes problems seem manageable, concerns less overwhelming. The Milky Way's disk is incredibly thin relative to its width. The galaxy spans 100,000 light-years across, but only about 1,000 light-years thick in most places, a ratio of 100 to 1. If you scaled the Milky Way down to the size of a dinner plate, its thickness would be comparable to a sheet of paper. This extreme flatness results from rotation and angular momentum. Stars orbiting in roughly the same plane, creating a disk-like pizza dough spun by a cosmic chef. This thinness means most of the galaxy is empty space above and below the disk. The galactic haloospherical region containing old stars and globular clusters surrounds the disk. But the disk itself is where most stars reside, where most action occurs, where you find star formation, spiral arms, planets, and presumably life. Looking up on a dark night, you're seeing this disk edge on. The Milky Way band stretching across the sky is your view through the disk's width, stars stacked billions deep in your line of sight. Looking perpendicular to the Milky Way band, you're viewing the galaxy's thin dimension, fewer stars in that direction. Clearer views of intergalactic space, windows onto the universe beyond our galaxy. This geometry affects astronomy. In the plane of the Milky Way, dust obscures distant objects. The view through the disk is murky, filled with intervening material. Above and below the galactic plane, views are clearer, allowing telescopes to peer deep into intergalactic space, observing distant galaxies billions of light years away with minimal interference from our own galaxy's dust. Your vocation within this disk shapes what you see. Standing on Earth's surface, looking up, you're embedded in the disk looking through it. Your view fundamentally different from hypothetical observers above or below the galaxy who could see the entire spiral, structure spread out like a cosmic pinwheel. The galactic center harbors a supermassive black hole called Sagittarius A*, pronounced Aster. This monster contains about 4 million times the Sun's mass compressed into a region smaller than Mercury's orbit. It's a gravitational beast, invisible itself, but revealing its presence through stars orbiting at thousands of kilometers per second, racing around the unseen mass at speeds that would tear planets apart. This black hole isn't actively feeding much currently. It's relatively quiet, a sleeping giant surrounded by orbiting stars, occasionally swallowing gas clouds or unfortunate stars, but mostly dormant. In the past, it may have been more active, blazing as a quasar, outshining the entire galaxy as matter spiraled inward, heated to millions of degrees, and blasted radiation across space. Sagittarius A* is 26,000 light-years away. At that distance, even this 4 million solar mass monster appears tiny in Earth's sky, smaller than a grape on the moon as seen from Earth, but its gravitational influence extends across thousands of light-years, organizing the central bulge, affecting orbits of millions of stars, creating the dynamical core around which the entire galaxy rotates. You're orbiting this black hole right now. Your circular path around the galactic center is determined ultimately by Sagittarius A*, and the surrounding mass, the black hole's gravity, plus the gravity of millions of central stars, creating the gravitational well we orbit within. You're a moon to this black hole's planet, circling at tremendous distance, but bound nevertheless by its gravitational reach. Black holes sound terrifying, but at safe distances, they're benign. Sagittarius A*, poses no threat to Earth. We're too far away, our orbit stable, the black hole too small and distant to affect us. It's a gravitational anchor, central mass holding the galaxy together, playing a constructive rather than destructive role in our cosmic neighborhood. The Milky Way collides with nothing currently, but will merge with Andromeda. Our nearest large galactic neighbor, the Andromeda Galaxy, approaches at about 110 kilometers per second, rushing toward us through intergalactic space. In approximately 4.5 billion years, the two galaxies will collide. Not in catastrophic crash, but in slow motion, cosmic merger spanning hundreds of millions of years. Despite billions of stars in each galaxy, stellar collisions will be rare. Stars are so small and widely spaced that two galaxies can interpenetrate with almost no direct collisions. Like two swarms of gnats passing through each other, individuals rarely touching despite the swarms occupying the same space. Gravity will reorganize everything. Stars flung into new orbits, spiral structures destroyed and reformed, the two galaxies gradually merging into single elliptical galaxy. Earth and the solar system will likely survive intact. We might be flung into different orbit, perhaps farther out, perhaps ejected entirely into intergalactic space. but the sun and its planets should remain gravitationally bound to each other. Our small system persisting even as the larger galactic structures reorganize around us. The night sky will be spectacular during the merger. Andromeda will grow from faint smudge to dominant feature, eventually filling the sky. Stars from two galaxies mingling overhead, new star formation triggered by gas clouds colliding, brilliant blue clusters of young stars scattered across the heavens. It will be cosmic fireworks, show lasting millions of years, visible throughout the merger to any beings present to witness it. But this is 4.5 billion years, a way longer than Earth has existed, longer than life has flourished, longer than the sun will remain stable. The merger is real and inevitable, but so distant in time that it's essentially separate from current concerns. Belonging to a future so remote, it might as well be another universe. The Milky Way's spiral arms are not permanent structures. Unlike rigid spokes on a wheel, spiral arms are density waves regions, where stars and gas temporarily concentrate as they orbit, creating appearance of continuous structure, even though individual stars drift in and out of the arms over millions of years. It's like traffic jam on a highway. The jam persists even though individual cars move through it, slow motion creating the appearance of stationary obstacle. Stars orbit faster than spiral arms rotate. As stars overtake the density wave, they slow down slightly due to increased gravitational density, creating temporary concentration. After passing through, they speed up again, moving ahead until they lap the slower rotating wave and enter it again from behind. This mechanism maintains spiral structure despite differential rotation that should wind everything up into tight spiral after a few orbits. The spiral arms are where star formation happens. Compression as material enters the density wave triggers collapse of gas clouds, initiating star formation, creating bright blue stars that trace out the spiral arms. These massive young stars are short-lived. They form, burn brightly for a few million years, then explode as supernova, all while still near their formation site within the spiral arm. That's why spiral arms appear blue. They contain young stars, stellar nurseries, regions of active creation. Our solar system lies between major spiral arms. We're in the Orion arm, a minor structure connecting the Sagittarius and Perseus arms, a bridge, rather than a major arm, a secondary feature in the galactic structure. This location is relatively quiet, star formation proceeding gently. Fewer massive stars nearby to threaten us with radiation or supernova explosions. Quiet locations favor life. The major spiral arms are turbulent, filled with massive stars, frequent supernova, intense radiation. Life might struggle to establish itself in such environments, constantly disrupted by cosmic catastrophes. Our location between major arms in a relatively peaceful region.
If you enjoy
may
these
have been
cosmic
crucial
whispers,
for life's
a gentle
emergence
like helps
and
others find their
evolution
way to
on Earth.
peaceful.
The galactic bulge contains old yellow stars. This central swelling, about 10,000 light-years in diameter, hosts ancient stars dating back to the galaxy's early history. These stars are red and yellow rather than blue. Their ages measured in billions rather than millions of years. Their orbits often chaotic rather than neatly circular like stars in the disk. The bulge is crowded. Stars pack much more densely there than in our neighborhood. Spacing between stars might be only a few light months rather than our local several light years. The night sky viewed from a bulge planet would be magnificent. Thousands of stars visible to the naked eye, some bright enough to cast shadows. The sky never truly dark, even on moonless nights. But the bulge might not favor life. Radiation levels are higher there, supernova more frequent, gravitational perturbations from passing stars potentially disrupting planetary systems. The crowded conditions that create beautiful night skies might make stable planetary systems rare. Long-term biological evolution difficult. You inhabit the galaxy's suburbs, not the crowded urban core, not the empty rural outskirts, but the comfortable suburbs populated enough to be interesting, sparse enough to be safe, positioned optimally for life's emergence and persistence. Your location is cosmically fortunate, whether through anthropic selection or genuine luck. The Milky Way is part of the local group. This collection of about 80 galaxies stretches across 10 million light-years, dominated by 3 large spirals, the Milky Way, Andromeda, and Triangulum, plus dozens of smaller dwarf galaxies gravitationally bound to the larger members. It's a small cluster by cosmic standards, a quiet galactic neighborhood where things proceed relatively calmly. The local group is gravitationally bound, despite cosmic expansion causing distant galaxies to recede. Local group members will never separate. Their mutual gravity is strong enough to overcome expansion, keeping them together, eventually causing them to merge. In the far future, the local group may become single, giant, elliptical galaxy, merger of all current members, sole remaining structure in an increasingly empty universe as expansion carries other galaxy groups beyond the cosmic horizon. Most local group mass is dark matter. The visible stars and gas comprise only about 10% of the total mass. The rest is invisible dark matter, detected only through gravitational effects. This dark matter provides the gravitational glue holding the local group together, creating the structure within which galaxies form and evolve. The Milky Way is the local group's second largest galaxy. Andromeda is larger, containing perhaps 1 trillion stars compared to our few hundred billion. But the Milky Way is substantial, comparable to Andromeda. The 2 spirals paired like binary stars, their fates intertwined, their eventual merger inevitable. You inhabit one member of a small cosmic community, not alone in the universe, but part of group, one galaxy among several dozen. Your existence enabled by the gravitational environment created by this local clustering. Isolation and community coexist at cosmic scales. The local group is isolated from other groups by vast distances, yet internally connected by gravity. The Milky Way formed about 13.6 billion years ago. Only a few 100 million years after the Big Bang, the first stars began forming in the region that would become our galaxy. Over billions of years, multiple smaller structures merged, gradually building the Milky Way. We see today a spiral galaxy assembled through countless mergers, collisions, and accretions of smaller systems. This makes the Milky Way younger than the universe, but not by much. The universe is 13.8 billion years old. Our galaxy is 13.6 billion years old. The Milky Way is a first-generation galaxy, formed early in cosmic history when the universe was still young and galaxies were just beginning to coalesce from the primordial dark matter structures. The galaxy hasn't been static. Its structure has evolved over billions of years, spiral arms forming and dissolving, star formation rates varying, minor galaxies merging into it, the central black hole growing through accretion. What we see now is a snapshot of ongoing evolution, not final form, but current state in continuous process. The Sun formed about 8 billion years after the galaxy. Our solar system is relatively young by galactic standards. Third-generation star system, born from material enriched by previous stellar generations. The heavy elements in your body, carbon, oxygen, nitrogen, everything except hydrogen and helium, were created by earlier stars, cycled through multiple stellar generations before being incorporated into the Sun, Earth, and you. Your late arrival to the galactic story. The Milky Way existed for billions of years before Earth formed, will persist for billions after Earth is gone. Your brief chapter in longer tale, temporary manifestation of matter, briefly organized into conscious form, experiencing galaxy in its middle age. The Milky Way contains globular clusters. These ancient spherical collections of stars, typically containing hundreds of thousands to millions of stars, packed into regions only tens of light years across orbit the galaxy in the stellar halo. About 150 known globular clusters surround the Milky Way. Relics from the galaxy's early history, fossils of conditions when the universe was young. Globular cluster stars are old, red, and metal poor. They formed when the galaxy was young, before multiple stellar generations had enriched space with heavy elements. These stars contain mostly hydrogen and helium, the primordial elements from the Big Bang, with only traces of heavier elements created by the very first stellar generations. The night sky from a globular cluster planet would be extraordinary. Stars packed so densely that thousands would be visible to the naked eye, many bright enough to read by at night, the sky filled with light, even on moonless nights. But such planetary systems are probably rare. The dense stellar environment makes stable orbits difficult. Gravitational perturbations from passing stars, potentially disrupting planets. Globular clusters orbit in the halo, unlike disk stars orbiting neatly in the galactic plane. Globular clusters follow elliptical orbits tilted at various angles, plunging through the disk, then soaring above it, spending most time in the diffuse halo surrounding the galaxy. They're satellites of the Milky Way, orbiting like moons around a planet, bound by gravity, but not part of the main disk structure. These clusters are laboratories for studying stellar evolution. All stars in a globular cluster formed at roughly the same time from the same material like siblings, same age and composition. This allows astronomers to test theories of stellar evolution, seeing how stars of different masses age, comparing observation to theory, confirming our understanding of how stars live and die. The Milky Way is eating smaller galaxies. Right now, several dwarf galaxies are being consumed, their stars stripped away by the Milky Way's tidal forces, their substance incorporated into our galaxy. The Sagittarius dwarf elliptical galaxy is currently merging with the Milky Way, stretched into long stream of stars wrapping around the galaxy, gradually being assimilated. This cannibalism is normal. Large galaxies grow by consuming smaller ones, hierarchy of mergers, where small structures combine into larger ones, gradually building the massive galaxies we see today. The Milky Way has consumed dozens of smaller galaxies over its history, each merger adding mass, possibly triggering star formation, contributing to the galaxy we observe now. These mergers are visible in stellar streams. Long filaments of stars stretching across the sky mark the tidal debris of disrupted dwarf galaxies, trails of breadcrumbs showing where galaxies fell apart. Astronomers can study these streams to reconstruct the Milky Way's merger history, determining when different dwarf galaxies were consumed, mapping the assembly history of our galaxy. You live in a cannibal galaxy. The beautiful spiral structure around you was built partly through violent consumption of smaller systems. Beauty created through destruction, order arising from chaos. This is how structure forms in the universe, through gravity, pulling things together. Larger things, absorbing smaller things. Hierarchy, building from bottom up, through countless mergers. Yet despite the violent language, these mergers are gentle by human standards. No explosions, no catastrophic crashes, just slow gravitational interaction over millions of years. Stars gradually redistributed, orbits slowly altered, structures patiently reorganized. Violence at cosmic scales is gentle, destruction proceeding slowly enough to appear almost serene. The Milky Way's dark matter halo is 10 times more massive than all the stars. This invisible substance, detected only through gravitational effects, surrounds and permeates the galaxy, providing most of the gravitating mass, creating the gravitational potential well within which the visible galaxy sits. The stars you see are just the bright tip of a much larger, mostly invisible structure. Dark matter doesn't emit, absorb, or reflect light. It interacts only through gravity and possibly through unknown forces undetectable by current instruments. It's invisible, intangible, mysterious yet undeniably present. Its gravitational effects observed in galactic rotation curves, gravitational lensing, and large-scale structure formation. The dark matter halo extends far beyond the visible disk, while the starry disk ends at about 50,000 light-years from the galactic center. The dark matter halo continues to perhaps 500,000 light-years or more, 10 times farther, creating enormous sphere of invisible mass surrounding the visible galaxy like fog around a streetlight. This dark matter-enabled galaxy formation. Without it, the ordinary matter wouldn't have clumped strongly enough to form galaxies. The universe would be nearly uniform, with only slight density variations, rather than the rich structure we observe. Dark matter provided the gravitational scaffolding onto which ordinary matter fell, creating the galaxies, clusters, and cosmic web visible today. You're embedded in dark matter. It passes through Earth, through you, constantly particles streaming through your body without interacting. Ghostly presence, detectable only through gravity. You're bathed in dark matter, swimming through an invisible ocean, yet you feel nothing. It's there, all around you, yet utterly inaccessible to direct experience. Let your breathing slow to match the gentle pace of galactic rotation. Slow, deep breaths, like the patient orbits of stars around the galactic center, measured in millions of years, yet proceeding inevitably, patiently, without rush or urgency. The Milky Way rotates differentially like a whirlpool. Inner regions orbit faster than outer region stars near the galactic center, complete their circuits in only a few million years, while we in the outer regions take 225 million years. This differential rotation creates the spiral structure, material flowing at different speeds, creating density waves that sweep around the galaxy like ripples in a cosmic pond. If the galaxy rotated like a solid wheel, spiral arms would wind up tightly after a few rotations, becoming so tightly wound they'd disappear. Instead, the density wave theory explains how spiral structure persists. The wave pattern rotates slower than the stars, allowing stars to enter and exit arms, while the arms themselves maintain their structure over billions of years. This differential rotation creates sheer adjacent regions, moving at different speeds, create friction-like effects in the interstellar gas, generating turbulence, possibly triggering star formation, creating complex dynamics in the gas that fills space between stars. It's like ocean currents, creating eddies and whirlpools, different flow speeds, creating structure from chaos. You're moving at a different speed than the galactic center. Your orbital velocity, 230 kilometers per second, is much slower than stars closer in, much faster than stars farther out. You're part of the differential rotation, one element in the galaxy's whirlpool flow. Your motion contributing to the overall pattern, even though you can't perceive it. This motion is ancient and ongoing. The Sun has circled the galaxy 18 to 20 times since forming, each orbit taking over 200 million years. Motion continuing for billions of years before, and presumably billions of years after. You're part of a process that predates Earth's existence and will continue long after. Earth is gone temporary passenger on an eternal cosmic carousel. Star formation continues actively in the Milky Way. About 3 solar masses worth of new stars form each year, equivalent to 3 suns worth of material collapsing from gas clouds into stellar infants. This seems like a lot until you realize it's spread across the entire galaxy. Star formation is common but not concentrated, happening in pockets scattered across the spiral arms and disk. Most star formation occurs in giant molecular clouds. These enormous clouds of hydrogen gasum containing millions of solar masses are the nurseries where stars are born, cold and dense, shielded from starlight by their own opacity. These clouds fragment under their own gravity, pieces collapsing into protostars that eventually ignite as hydrogen fusion begins. The Orion Nebula is the closest active star-forming region, located about 1,350 light-years away, visible to the naked eye as the fuzzy middle star in Orion's sword. This stellar nursery is creating hundreds of new stars right now. Through telescopes, it reveals clouds of glowing gas illuminated by newly formed stars. Pillars of dense material where stars are actively coalescing, beauty created through stellar birth. Star formation is messy and violent. Young, massive stars emit intense radiation that heats and ionizes surrounding gas, creating glowing nebulae. Stellar winds and supernova explosions from the most massive stars blow bubbles in the interstellar medium, dispersing leftover gas and preventing further star formation nearby. Birth and destruction occur together, creation requiring the tearing apart of the maternal cloud. You're made from star-forming regions. The atoms in your body were once part of molecular clouds, like those forming stars today. Before the Sun formed 4.6 billion years ago, your atoms existed as cold gas in some ancient nebula, destined to collapse, heat up, form the Sun and planets, eventually being incorporated into living beings capable of contemplating their own origins. The Milky Way contains approximately 10 billion Earth-like planets. This estimate, based on exoplanet surveys around nearby stars, suggests that about 10% of Sun-like stars host planets in their habitable zones, the region where liquid water could exist on a planet's surface. With hundreds of billions of stars in the galaxy, even this conservative percentage yields billions of potentially habitable worlds. Most of these planets orbit stars we'll never visit. Even the nearest is over for light years, away for years of travel at light speed. decades or centuries at achievable spacecraft velocities. The vast majority are thousands or tens of thousands of light years distant, separated from us by gulfs so vast that communication, let alone visitation, is effectively impossible. Some of these planets might harbor life, perhaps simple bacteria-like organisms, perhaps complex ecosystems, perhaps intelligent civilizations. We don't know. Despite decades of searching, we found no definitive evidence of extraterrestrial life. The galaxy might be teeming with life, or might be nearly empty. Both possibilities are consistent with current evidence. The Fermi paradox asks, if intelligent life is common, where is everyone? With billions of potentially habitable planets and billions of years for life to evolve, why haven't we detected alien civilizations? The silence might mean intelligence is rare, or space is too vast for contact, or civilizations destroy themselves quickly, or we're looking in the wrong ways. The question remains open, simultaneously hopeful and lonely. You might be the only conscious being currently existing in the Milky Way, or you might be one of trillions, scattered across countless worlds, most never communicating, existing in isolation despite shared galactic homes. Either answer is profound. Uniqueness carries responsibility. Plurality offers connection. The uncertainty itself is part of the mystery. The interstellar medium fills space between stars. This tenuous gas, mostly hydrogen, with traces of heavier elements and dust grains, occupies the volume between stellar systems. Average density of about 1 atom per cubic centimeter. It seems empty by terrestrial standards, yet contains most of the galaxy's normal matter, not locked up in stars. This medium is not uniform, but structured. Hot bubbles blown by stellar winds, cool, dense clouds, where stars form, warm, diffuse gas, filling the space between. Shocked regions compressed by supernova blast waves, all coexist, creating complex ecology of interstellar matter at various temperatures, densities, and states. The Sun is currently passing through a structure called the local bubble. This region of hot, low-density gas, about 300 light-years across, was probably created by multiple supernova that exploded millions of years ago, heating and expanding the local interstellar medium, creating a bubble that we're still moving through. Within the local bubble exists the local interstellar cloud, an even smaller structure, only a few light-years across. The Sun entered this cloud a few thousand years ago and will exit in perhaps 10,000 to 20,000 years. On human timescales, this seems eternal. On cosmic timescales, it's a brief passage, moment in the Sun's long journey through varying interstellar environments. These structures affect Earth subtly. The density and properties of the interstellar medium the Sun moves through affect the heliosphere, the bubble of solar wind surrounding the solar system, which, in turn, affects the cosmic ray environment at Earth. Changes in interstellar conditions might correlate with climate variations over millions of years, though the effects are small and controversial. Cosmic rays permeate the galaxy. These high-energy particles, mostly protons, some heavier nuclei, travel through space at near light speed, created by supernova explosions, possibly accelerated by other energetic processes. They carry enormous energy. Individual particles, sometimes having more energy than a thrown baseball, despite being subatomic in size. These particles constantly bombard Earth. About 1 cosmic ray particle hits each square centimeter of the upper atmosphere every second. They create showers of secondary particles when they collide with air molecules, occasionally reaching the ground, passing through your body, occasionally damaging DNA or electronics through their high energy. Cosmic rays affect atmospheric chemistry. They ionize air molecules, creating nucleation sites for cloud formation, possibly affecting climate. Some scientists speculate that cosmic ray variations modulated by solar activity and the interstellar medium's density might influence Earth's climate over geological timescales, though this remains debated. The galaxy's magnetic field channels cosmic rays. This weak but extensive field, about a millionth the strength of Earth's magnetic field, pervades the interstellar medium, shaping cosmic ray paths, influencing their distribution, affecting how they reach the solar system. The field is generated by complex processes involving rotating plasma and the galaxy's overall dynamics. You're shielded from the most dangerous cosmic rays by Earth's magnetic field and atmosphere. The particles that reach ground level have been significantly moderated, their energy reduced by atmospheric interactions, their flux limited by magnetic deflection. Without these protections, cosmic rays would make Earth's surface hostile to life. Their radiation damage overwhelming biological repair mechanisms. The Milky Way contains nebulae of stunning beauty. These clouds of glowing gas, illuminated by nearby stars, shaped by stellar winds, colored by emission from different elements, are among the galaxy's most photogenic features. Though faint, invisible light, long-exposure photographs reveal structures of breathtaking complexity and color. The Eagle Nebula hosts the pillars of creation. These towering columns of gas and dust teach several light years tall, comparable to the distance from Sun to the nearest stars, actively forming stars. Dense knots within the pillars are protostars, embryonic suns, still gathering mass, not yet hot enough to shine, but destined to ignite eventually. The Carina Nebula harbors some of the galaxy's most massive stars. Eta Carini, a hypergiant star over 100 times the Sun's mass, dominates this region, its intense radiation sculpting the surrounding gas into bizarre shapes. This star is unstable, prone to violent outbursts, expected to explode as a supernova sometime in the next million years soon by astronomical standards. The Helix Nebula shows a star's death throes. This planetary nebula formed when a sun-like star shed its outer layers at the end of its life, peers as a giant cosmic eye when photographed. The dying star's exposed core, now a white dwarf, illuminates the expanding shell of ejected material, creating the ghostly appearance. These nebulae are both beautiful and functional. They recycle stellar material back into the interstellar medium, enriching space with heavy elements created by stellar nucleosynthesis and supernova explosions. There, where old stars return their substance to the galaxy, making that material available for future star and planet formation. The galactic disk is warped like a potato chip. Instead of being perfectly flat, the disk curves up on one side and down on the other, creating a subtle S-shape. This warp extends to the galaxy's outer regions, becoming more pronounced at greater distances from the center where the disk's self-gravity is weaker. The warp might result from interactions with satellite galaxies. The large and small Magellanic Clouds dwarf galaxies orbiting the Milky Way exert tidal forces that could warp the disk, their gravity pulling harder on the nearest parts of the disk than on the farthest parts, creating the observed distortion. Or the warp might be caused by dark matter halo asymmetries. If the dark matter distribution isn't perfectly spherical, its gravitational influence could differentially affect different parts of the disk, creating warp. The exact cause remains uncertain. Multiple mechanisms might contribute simultaneously. Measuring the warp required careful three-dimensional mapping. For decades, astronomers knew the Milky Way was warped but couldn't determine the warp's exact shape. Recent surveys using variable stars as distance indicators have finally mapped the warp in detail, revealing its complexity. You're part of this warped structure. The disk you orbit within isn't flat but curved. The plane of your orbit tilted relative to distant regions. The warp is subtle. The disk's thickness is far less than the warp's amplitude but real. Another example of how actual galaxies are messier and more complex than idealized models suggest. The Milky Way is moving through space at 630 kilometers per second. This motion isn't orbital, but bulk flow. The galaxy and its neighbors are all streaming toward a structure called the Great Attractor. A massive concentration of galaxies, about 150 million light-years away. Everything in our cosmic neighborhood participates in this flow, carried along by gravity's influence across vast distances. Beyond the Great Attractor lies the Shapley supercluster. This enormous concentration of galaxies, one of the largest structures in the observable universe, may be the ultimate destination toward which we're being pulled. Or perhaps even larger structures affect our motion. Gravitational influences extending across hundreds of millions of light-years, creating flows too vast to easily measure. This motion is invisible from Earth. Everything nearby moves together. The sun, nearby stars, the entire local groups, so there's no relative motion to observe. Only by measuring the cosmic microwave backgrounds, dipole patterns, light temperature variations caused by our motion relative to the radiation filling space can we determine our velocity through the universe. You're moving at 630 kilometers per second through intergalactic space. Added to Earth's orbital motion around the sun's motion around the galactic center, and the galaxy's motion through the local group. Your total motion through space involves multiple velocity vectors pointing in different directions, their combination determining your absolute motion through the cosmos. Yet you feel none of this motion. All velocities are smooth, no acceleration, no sensation of movement. You rest peacefully while hurtling through space at speeds that would vaporize any material object if air resistance existed at those velocities. The stillness you experience is relative, not absolute. Motion and rest depend on reference frame. The Milky Way's oldest stars are nearly as old as the universe. Some halo stars formed within a few 100 million years of the Big Bang, when the universe was still in its infancy, before the Milky Way had fully assembled. These ancient suns have burned steadily for over 13 billion years, witnesses to almost the entire cosmic history. These old stars are metal poor. They contain mostly hydrogen and helium, with only traces of heavier elements, carbon, oxygen, iron, because they formed before multiple stellar generations had enriched space with the products of stellar nucleosynthesis. Studying their composition reveals conditions in the early universe before elements heavier than helium were common. The oldest stars are small and red. Massive stars burn quickly. The most massive live only millions of years before exploding as supernova. Only small stars, less massive than the sun, live long enough to survive from the galaxy's early history to today. These elderly stars are dim, cool, barely visible, yet they're among the galaxy's most valuable fossils. Globular clusters contain many of these ancient stars, because cluster stars all formed together. Measuring one star's age tells you the cluster's age, which provides a minimum age for the galaxy itself. The oldest globular clusters date to about 13 billion years ago, setting a lower limit on the Milky Way's age. You're made of material. These stars produced, even the oldest stars, contain traces of heavier elements created by an even earlier generation, the population. 3 stars that formed from pure Big Bang material and produced the first heavy elements through fusion and supernova explosions. Multiple stellar generations separate you from the Big Bang. Your atoms cycled through several stars before being incorporated into the Sun and Earth. The Milky Way contains about 50 billion white dwarfs. These stellar corpses, the exposed cores of dead sun-like stars, populate the galaxy in vast numbers, most too dim to detect individually, but contributing significantly to the total mass. Each represents a star that lived its life, shed its outer layers, and left behind a dense remnant, slowly cooling over trillions of years. White dwarfs are incredibly dense. A teaspoon of white dwarf material weighs about 5 tons the mass of an elephant compressed into a sugar cube's volume. This density results from quantum degeneracy, pressure electrons packed so tightly that quantum mechanics prevents further compression, creating material unlike anything on Earth. These objects are the Sun's future fate. In about 5 billion years, the Sun will exhaust its hydrogen fuel, swell into a red giant, shed its outer layers as a planetary nebula, and leave behind a white dwarf about Earth size, containing half the Sun's original mass. This remnant will gradually cool, fading over trillions of years, but never truly dying, persisting as stellar ember long after all nuclear burning has ceased. White dwarfs eventually become black dwarfs. After cooling for trillions of years longer than the current age of the universe, they'll radiate away all remaining heat, becoming dark, cold, dead objects. The universe isn't old enough for any black dwarfs to exist yet, but in the far future, they'll be common, perhaps the most numerous stellar remnants. Your ultimate fate is connected to white dwarfs. When the Sun becomes a white dwarf, Earth might survive as a charred cinder in distant orbit, or might be engulfed during the red giant phase, or might be ejected into interstellar space by gravitational perturbations. Either way, the atoms comprising your body will persist, scattered, perhaps, but not destroyed, eternal in their way, even as their temporary organization you has long since dissolved. The galactic halo contains mysterious stellar streams, these long, thin filaments of stars stretching across the sky are tidal debris from disrupted dwarf galaxies and globular clusters, torn apart by the Milky Way's gravity over hundreds of millions of years. They're like cosmic breadcrumbs, trails showing where smaller systems have been consumed. The Sagittarius stream is the most prominent. This tidal tail from the Sagittarius dwarf, elliptical galaxy currently merging with the Milky Way wraps completely around the galaxy, visible as a river of stars flowing through the halo. The stream reveals the orbit along which the dwarf galaxy fell into the Milky Way, evidence of ongoing galactic cannibalism. These streams help map the dark matter distribution. Their shapes and motions are determined by the Milky Way's gravitational field, which depends on both visible and dark matter. By measuring stream properties and comparing to simulations, astronomers can infer the dark matter halo's shape and mass. using tidal debris as tracers of invisible matter. Dozens of streams have been discovered. Each represents a destroyed satellite consumed by the Milky Way over its history. Some are recent stars, still clumped together, not yet fully dispersed. Others are ancient stars, spread thin, barely distinguishable from the general halo population. Ghost structures, marking long-ago mergers. You orbit through a galaxy built from mergers. The smooth spiral structure, visible on dark nights, is recent configuration, temporary arrangement of stars and gas that will change as future mergers occur. The Milky Way's history is violent, consuming smaller galaxies, incorporating their stars, yet the violence proceeds so slowly it appears serene. The Milky Way's magnetic field is weak but vast, about a millionth the strength of Earth's field. It nonetheless extends across the entire galaxy, pervading the disk, threading through the spiral arms, organizing charged particles over tens of thousands of light-years. This field is generated by complex dynamo processes involving the rotating, ionized interstellar medium. The field follows spiral structure. Magnetic field lines align with spiral arms, possibly helping to maintain them, definitely affecting how gas flows through the disk. The field channels cosmic rays, shapes supernova remnants, influences star formation by affecting how gas clouds collapse. Pulsars reveal the galactic magnetic field. These rapidly rotating neutron stars emit radio beams that sweep past Earth like lighthouse beams. The radio waves are affected by the interstellar magnetic field, their polarization and arrival times encoding information about the field they passed through. By studying hundreds of pulsars scattered across the sky, astronomers map the galactic magnetic field's structure. The field's origin is partially mysterious. Amplifying weak seed fields from the early universe through dynamo action is theoretically possible, but the details of how the galaxy's field achieved its current strength and structure remain uncertain. Magnetic field generation in galaxies is an active research area, combining observations, simulations, and theory. You're embedded in this magnetic field. It passes through you constantly, too weak to affect biological processes directly, yet shaping the environment you inhabit by affecting cosmic rays, organizing interstellar matter, influencing the space weather that Earth occasionally experiences when solar storms interact with Earth's magnetic field. The galaxy contains millions of neutron stars. These incredibly dense stellar remnants formed when massive stars explode as supernovae pack more mass than the Sun into a sphere only 20 kilometers across. Their density is so extreme that their matter is compressed into exotic states, neutrons packed together, nuclear forces preventing further collapse, creating the densest stable matter possible. Most neutron stars are invisible. They emit little light and are incredibly small, difficult to detect unless they're actively accreting material or beaming radiation toward Earth as pulsars. The millions estimated to exist based on supernova rates are mostly hidden, dark objects drifting through the galaxy undetected. Some neutron stars are pulsars. These rapidly spinning neutron stars emit beams of radio waves from their magnetic poles. As the star rotates sometimes hundreds of times per second, the beam sweeps across space like a lighthouse, creating precisely timed pulses detectable across interstellar distances. Over 2,000 pulsars are known in the Milky Way, likely representing only a fraction of the total. Neutron star matter is bizarre beyond comprehension. At the surface, Gravity is 200 billion times stronger than Earth's a falling object would hit the surface at a significant fraction of light speed. The interior contains neutrons packed together, possibly forming exotic states like neutron superfluids or quark matter. Physics operates at extremes impossible to recreate in laboratories. You're made of matter that might someday exist in neutron stars. If the sun were massive enough to explode as a supernova, which it isn't, its core would collapse into a neutron star, crushing electrons, creating neutrons, compressing everything to nuclear density. Your atoms would be crushed beyond recognition, their individuality destroyed, contributing to a stellar corpse so alien it barely resembles matter as you know it. The Milky Way rotates once every 225 million years at the sun's distance. But this isn't a universal rotation period. The galaxy doesn't rotate as a solid wheel. Instead, different regions orbit at different speeds, creating the differential rotation that maintains spiral structure and drives galactic dynamics. This rotation is sustained by gravity, the combined mass of all stars, gas, dark matter, and the central black hole creates gravitational field that determines orbital velocities at each distance. By measuring rotation speeds and applying Newton's laws, astronomers can weigh the galaxy, determining its total mass, including invisible dark matter. The rotation curve stays flat at large distances. In the outer galaxy, where visible matter becomes sparse, orbital velocities remain constant rather than decreasing as expected if only visible matter existed. This flat rotation curve is primary evidence for dark matter. Invisible mass must exist to explain why outer regions orbit so quickly. This discovery revolutionized cosmology. Vera Rubin and Kent Ford's measurements of galactic rotation curves in the 1970s provided compelling evidence that galaxies contain far more mass than visible stars and gas can account for. Dark matter went from speculation to established fact, transforming our understanding of cosmic composition. You orbit within the region where rotation curves are well measured. The sun's orbital velocity, 230 kilometers per second, is known precisely, constrained by observations of nearby stars and gas clouds. This velocity, combined with the distance from galactic center, determines the mass interior to our orbit, providing handle on how much dark matter exists in the inner galaxy. Let your mind drift like gas clouds through the galaxy. Slow, purposeless wandering, flowing with cosmic currents, no destination, just gentle motion through space and time, peaceful as interstellar wind. The Milky Way's spiral arms are named Perseus, Sagittarius, Coronal, Sagittarius, Scutums, Centaurus. These major arms wind around the galaxy like ribbons around a maypole. The sun orbits in the Orion Arm, a minor structure connecting the Sagittarius and Perseus arms, sometimes called the Orion Spur Bridge rather than a major arm. These names are human constructs. The galaxy knows no divisions, recognizes no boundaries. Spiral arms are concentrations along continuums, denser regions within gradients. Features we identify and name for convenience, but which blend smoothly into surroundings. Nature is continuous. Categories are our imposition. The arms contain the galaxy's star-forming regions, bright blue stars, glowing nebulae, giant molecular clouds all concentrate in spiral arms, where gas compression triggers star formation. The arms appear bright and blue because they contain young, massive, short-lived stars that haven't yet migrated away from their birthplaces. Between arms, regions are quieter. Star formation proceeds more slowly. Older yellow and red stars dominate. Gas is less dense. These interarm regions are where the sun resides, away from the tumultuous star-forming zones, in relatively peaceful orbital environment, favorable for long-term planetary stability. You inhabit the quiet zone, not in the action, not in the chaotic star-forming arms, but in calmer region between them. This location may be cosmically important. Life might preferentially arise in such zones, away from disruptive supernova explosions and intense radiation of newly formed massive stars. The Milky Way is gradually running out of gas. Star formation consumes hydrogen, converting it into stars that lock away that material for billions of years. Though dying stars return some gas to the interstellar medium, massive stars consume more than they return, gradually depleting the gas supply available for future star formation. At current rates, the galaxy will exhaust its star-forming gas in a few billion years. After that, star formation will slow, then stop, the galaxy gradually reddening as massive blue stars die and aren't replaced, leaving only long-lived red and yellow stars aging toward their eventual deaths. The Milky Way will become a red and dead galaxy, star formation a thing of the past. But the Andromeda merger will change this. When the galaxies collide in 4.5 billion years, their gas clouds will compress, triggering vigorous starburst brief period of intense star formation, perhaps creating millions of new stars, temporarily rejuvenating both galaxies before gas is exhausted completely. The far future galaxy will be dimmer, redder, quieter, fewer stars, no new formation, gradually aging stellar population. It will persist for trillions of years, stars slowly dying one by one, the galaxy fading like embers in a dying fire, structure maintained by gravity long after all nuclear burning has ceased. You live in the galaxy's prime, star formation still active, young stars still forming, the Milky Way in its golden years, mature but vigorous, aged but productive. Billions of years from now, observers, if any exist, will look out on dimmer, older galaxy, its youth vanished, its star-forming days ended. The galactic center is invisible light. Thousands of light years worth of interstellar dust block our view, absorbing and scattering visible photons, creating a dark zone where we cannot see through to the core. Standing on Earth and looking toward the constellation Sagittarius, you're peering toward the galaxy's heart, but seeing only nearby stars and dust, the center hidden behind cosmic fog. Infrared light penetrates the dust. At longer wavelengths, dust becomes transparent, allowing infrared telescopes to peer through to the galactic center. These observations reveal a crowded, chaotic regions, stars packed millions of times more densely than in our neighborhood, orbiting the central black hole at tremendous speeds, creating one of the most exotic environments in the galaxy. Radio waves also penetrate the dust. Radio telescopes detect Sagittarius A*, the supermassive black hole, through radio emissions from hot gas near the event horizon. They also reveal complex structures, filaments of magnetized gas, clouds of molecular material, regions of star formation proceeding despite the hostile environment. X-rays reveal the most violent processes, High-energy radiation from the galactic center shows gas heated to millions of degrees, possibly by shock waves or magnetic reconnection events. The X-ray view shows a galaxy far more active and violent than the visible light view suggests. Hidden processes revealed only through multi-wavelength observation. You're looking toward this hidden center every time Sagittarius is above the horizon. The galactic core lies in that direction, invisible in optical light, but there nonetheless, 26,000 light-years away, pulling you and the Sun in orbital motion, organizing the galaxy through its gravity, even though you cannot see it. The Milky Way has satellite galaxies. About 60 dwarf galaxies orbit our galaxy, gravitationally bound companions ranging from a few hundred light-years across to a few thousand. The largest are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as fuzzy patches of light, each containing billions of stars. The Magellanic Clouds are irregular galaxies. Unlike the Milky Way's organized spiral structure, these companions have chaotic shapes, star formation proceeding in bursts, structure determined more by past interactions than by internal dynamics. They're being tidally disrupted by the Milky Way's gravity. Streams of gas stripped away, their ultimate fate to be consumed by our galaxy. Most satellite galaxies are much smaller. Ultra-faint dwarfs contain only a few hundred to a few thousand visible stars, barely qualifying as galaxies, more like large star clusters. Yet they contain enormous amounts of dark matter, their total masses far exceeding their visible stellar content, making them among the most dark matter-dominated structures known. These satellites orbit in a puzzling configuration. Many lie in a single plane rather than being randomly distributed around the Milky Way as simulations predict. This plane of satellites problem is one of the tensions between observations and dark matter theory, possibly indicating we misunderstand satellite galaxy formation or dark matter's properties. You live in the dominant galaxy of a small group. The Milky Way is the largest or second largest galaxy in the local group. Its satellites orbiting like moons around a planet, their fates tied to ours. Their existence enabled by our gravitational embrace. Dominance and dependence coexist at galactic scales. Satellites depend on the Milky Way for gravitational stability, yet contribute to its mass and evolution. The Milky Way's escape velocity at the Sun's location is about 550 kilometers per second. Any object moving faster than this would escape the galaxy's gravity, leaving forever, no longer bound to the Milky Way. Below this speed, objects remain gravitationally bound, orbiting indefinitely or falling into the galaxy, captured by gravity's patient grip. Hypervelocity stars exceed this speed. These rare objects, perhaps ejected by interactions with the central black hole or by supernova explosions in binary systems, travel at up to 1,000 kilometers per second, fast enough to escape the galaxy entirely. They're cosmic outcasts, fleeing the Milky Way, destined to spend eternity in intergalactic space. About 24 hypervelocity stars.
If you enjoy these cosmic whispers,
they're difficult
a gentle light
to detect.
helps others find their way to peaceful.
Requires measuring both position and velocity precisely, distinguishing truly fast-moving stars from ordinary stars with unusual apparent motions. But they exist, testimony to violent processes capable of accelerating stars to galactic escape velocity. These stars will journey through intergalactic space forever. Having left the Milky Way, they'll eventually reach the space between galaxy groups, traveling through the cosmic voids, perhaps eventually being captured by another galaxy billions of years hence. They're interstellar wanderers on cosmic scale, homeless stars traveling the universe. You orbit well below escape velocity. The sun's orbital speed, 230 kilometers per second, is less than half the escape velocity, ensuring we remain gravitationally bound to the Milky Way. Earth is home. The sun is home. The galaxy is home. You're not escaping, not fleeing, but orbiting indefinitely within this stellar city. The Milky Way's metallicity increases toward the center. In astronomy, metals means all elements heavier than hydrogen and helium carbon, oxygen, iron, everything produced by stellar nucleosynthesis. The inner galaxy's stars contain more metals than outer regions, a gradient showing how stellar evolution and gas flows have distributed heavy elements across the disk. This metallicity gradient traces the galaxy's chemical evolution. Early in the galaxy's history, stars everywhere had low metallicity, containing mostly primordial hydrogen and helium. As stellar generations lived and died, supernova scattered heavy elements into the interstellar medium, enriching gas from which new stars formed. This process proceeded faster in the inner galaxy, where stars are denser and formation rates higher. The sun's metallicity is typical for its location. About 2% of the sun's mass is elements heavier than helium enough to form rocky planets, enable complex chemistry, support life. Stars closer to the galactic center have higher metallicity. Stars farther out have lower. We orbit in the Goldilocks zone, where metallicity is just right for terrestrial planet formation. Metallicity affects planet formation. Low metallicity stars form fewer rocky planets. Without heavy elements, only gas giants can form. High metallicity environments produce more planets, potentially including more Earth-like worlds. The metallicity gradient means the inner galaxy might have more terrestrial planets per star than outer regions. You're made of metals in the astronomical sense. Every atom in your body, except hydrogen, is a metal: carbon, oxygen, calcium, iron, all produced by stellar nucleosynthesis, scattered by supernova, incorporated into the molecular cloud that formed the sun. Your existence required stars to die, enriching space with the heavy elements necessary for planets and life. The Milky Way's stellar halo is spherical, while the disk is flat and rotating. The halo surrounds it as a spheroid, perhaps a somewhat flattened ellipsoid extending far beyond the visible disk, filled with old stars, globular clusters, and dark matter. This halo doesn't rotate like the disk, but contains stars on chaotic orbits, some plunging through the disk, others soaring far above it. Halo stars have high velocities relative to the disk, while disk stars orbit neatly in the galactic plane at a few hundred kilometers per second. Halo stars move in all directions at speeds up to several hundred kilometers per second. They're not participating in orderly galactic rotation, but following individual elliptical orbits determined by their formation conditions. The halo probably formed through mergers. Most halo stars likely originated in dwarf galaxies that merged with the Milky Way billions of years ago. Their stars scattered into the halo during the merger process. The halo is a fossil recorder, shredded remnants of ancient galaxies, their identities lost but their stars preserved, orbiting the Milky Way as testament to violent past. Some halo stars are extremely metal poor. These ancient objects contain less than 1,000th the Sun's metallicity, formed when the universe was very young, before many stellar generations had enriched space with heavy elements. They're the oldest stars we can study in detail, time capsules preserving information about conditions in the early universe. You're orbiting through a galaxy with complex history. The smooth spiral, visible on dark nights, is recent structure, temporary configuration masking violent past of mergers and disruptions. The Milky Way you see now is not how it always was or how it always will be, snapshot of ongoing evolution. The galaxy contains about 300 billion stars, according to recent estimates. This number is uncertain. Counting stars in a galaxy you're embedded within is difficult, like estimating the number of trees in a forest while standing among the trunks. But 300 billion is a reasonable middle estimate, accounting for all stellar types from massive blue giants to tiny red dwarfs. Most stars are red dwarfs. These small, cool stars, less than half the Sun's mass, are the galaxy's most common type, perhaps comprising 70% of all stars. They're dim and difficult to detect, but they're everywhere, outnumbering Sun-like stars by factors of hundreds, dominating the stellar population through sheer numerical superiority. Red dwarfs live for trillions of years because they burn hydrogen slowly. These miserly stars will outlive all other types, continuing to shine long after massive stars have exploded and sun-like stars have faded to white dwarfs. In the far future, red dwarfs will be the last stars shining, the galaxy's final embers, burning steadily in an otherwise dead universe. Some red dwarfs might host habitable planets, despite being cool and dim. Red dwarfs can maintain habitable zones, regions where liquid water could exist on planetary surfaces. Recent discoveries suggest that Earth-sized planets are common around red dwarfs, potentially providing billions of additional habitable worlds. You orbit a relatively rare star type. Sun-like yellow stars comprise less than 10% of the stellar population. The Sun is unusually large, unusually bright, unusually short-lived compared to the galactic norm. Your existence depends on this atypical star. Red dwarfs might not be suitable for life due to stellar flares and tidal locking of close-in planets. The Milky Way's central bulge rotates as a bar. This elongated structure, visible in infrared images that penetrate the dusties, about 27,000 light-years long and 13,000 light-years thick, rotating with a period of a few 100 million years. About 30% of spiral galaxies have such bars, making the Milky Way fairly typical in this regard. The bar affects spiral structure. It creates resonances that shape where spiral arms begin and how they develop. Organizes gas flows through the inner galaxy, possibly triggers star formation through compression, influences the entire disk's dynamics. The bar is not merely structural feature, but dynamical driver, active component shaping galactic evolution. The bar's formation is not fully understood. Galactic disks can develop bar instabilities spontaneously through gravitational interactions between stars, or bars can be triggered by interactions with satellite galaxies. Once formed, bars are usually stable, persisting for billions of years, slowly evolving as they exchange angular momentum with the surrounding disk. The bar affects gas flows toward the galactic center. Material can lose angular momentum through interactions with the bar, allowing it to spiral inward, potentially feeding the central black hole or triggering nuclear star formation. The bar acts as angular momentum transport mechanism, enabling matter to move inward that would otherwise remain at larger radii. You orbit outside the bar's extent. The bar dominates the inner several thousand parsecs. We're at about 8,000 parsecs from the center, well beyond the bar's direct influence. Our orbit is determined by the overall galactic mass distribution rather than by bar-specific effects, making our environment more stable and predictable. The Milky Way's total mass is about 1.5 trillion solar masses. This includes all stars, perhaps 300 billion solar masses plus gas and dust, about 10 billion solar masses plus the supermassive black hole, 4 million solar masses plus dark matter, comprising the rest. The majority of the galaxy's mass is invisible, detectable only through gravitational effects. This makes the Milky Way moderately massive. Some galaxies are 10 times more massive. Others are hundreds of times less massive. We inhabit a large galaxy, but not a giant, a significant member of the cosmic community, but not dominant at larger scales. Size is relative. What seems immense locally is moderate cosmically. Most of this mass extends beyond the visible stars. The dark matter halo stretches to perhaps 500,000 light-years, 5 times farther than the stellar disk containing most of the galaxy's mass in invisible form. The stars you see are just the bright center of a much larger, mostly dark structure. Measuring galactic mass is indirect. Astronomers use orbital velocities of stars and gas, motions of satellite galaxies, properties of stellar streamsol tracers responding to the total gravitational field. By measuring these motions and applying gravitational theory, the total mass can be inferred, even though most remains invisible. You're held by this mass. Your orbital motion is response to the Milky Way's gravitational field. The combined pull of 1.5 trillion solar masses keeping you in orbit, preventing escape, binding you to this cosmic structure. Gravity is relationship. You and the galaxy are connected through mutual gravitational influence. Though the galaxy's influence on you vastly exceeds yours on it. The Milky Way is about 13.6 billion years old. This age comes from studying the oldest stars in globular clusters, whose ages can be determined from their properties. These ancient stars formed when the galaxy was very young, within the first billion years of cosmic history, making the Milky Way one of the universe's early galaxies. The universe is 13.8 billion years old. The Milky Way formed only 200 million years after the Big Bang, late by cosmic standards, after the first stars, but early in the era of galaxy formation. The galaxy has existed for about 98% of cosmic history, witnessing the universe's evolution from young and chaotic to mature and structured. During the galaxy's lifetime, countless stellar generations have lived and died, massive stars forming, living, and exploding as supernova on timescales of millions of years. Hundreds of thousands of generations have come and gone since the galaxy formed. Each generation enriched space with heavy elements, gradually building up the metallicity we observe today. The Sun is a third-generation star. It formed about 8 billion years after the galaxy, from material enriched by 2 previous stellar generations. This multi-generation heritage is why Earth has the heavy elements necessary for rocky planets and life: carbon, oxygen, silicon, iron, all forged in earlier stars. You're a latecomer to the galactic story. The galaxy existed for billions of years before the Sun formed. will persist for billions after the sun dies. Your existence occupies a brief slice of galactic time, transient moment, in a story spanning almost the entire age of the universe. The Milky Way has experienced at least 10 major mergers. Throughout its history, the galaxy has consumed and absorbed numerous dwarf galaxies, each merger adding mass, possibly triggering star formation, contributing to the galaxy's growth. The current merger with the Sagittarius dwarf is the latest in a long series of cannibalistic events. Evidence for these mergers appears in stellar streams, long filaments of stars wrapping around the galaxy mark where dwarf galaxies were tidally disrupted, their stars scattered but still moving together along similar orbits. Each stream represents a destroyed galaxy, fossil of past violence. The Gaia space mission is revolutionizing merger archaeology. By precisely measuring positions and velocities of over 1 billion stars, Gaia allows astronomers to reconstruct the Milky Way's merger history, identifying groups of stars that originated in now destroyed satellites, tracing the accretion history that built the galaxy we see today. Some solar siblings might exist from disrupted clusters. The Sun formed in a cluster containing perhaps thousands of stars, which gradually dispersed over hundreds of millions of years. Some of those siblings might still exist, scattered across the galaxy, moving on similar orbits, unknowable without detailed analysis of stellar properties and trajectories. You're part of a galaxy built through violence. The peaceful appearance of the Milky Way on dark nights masks a history of mergers, disruptions, and accretions. Beauty built through chaos, order emerging from violence, structure created through destruction. These are the galaxy's founding principles. The galactic disk is about 1,000 light-years thick at the Sun's location. This thickness represents the vertical extent of the stellar disk, the distance from midplane to where star density drops significantly. It's thin compared to the disk's 100,000 light-year diameter, but still represents vast distance by human standards. 1,000 light-years is farther than humans will likely travel for millennia, if ever. The disk has two components, thin and thick. The thin disk, containing young stars and gas, is about 300 light-years thick. The thick disk, containing older stars, extends to about 1,000 light-years. These components have different origins. The thin disk from recent star formation, the thick disk possibly from ancient mergers or disk heating by past disturbances. The Sun orbits near the disk midplane. Our vertical position oscillates as we orbit. We pass through the midplane, rise about 70 light-years above it, fall back through, descend about 70 light-years below, then rise again, completing this vertical oscillation roughly every 30 million years while simultaneously circling the galactic center. This vertical motion exposes us to varying environments. Near the midplane, stellar and gas density is higher. Above or below, we encounter less material, fewer stars, clearer views of extragalactic space. These environmental changes might affect Earth's subtly cosmic ray fluxes, varying comet impacts, correlating with disk crossings. Though these effects are controversial and uncertain, you're currently near the disk midplane. The Sun is slightly above it, about 65 light-years, north, moving downward, destined to cross the midplane in a few million years, then continue downward before reversing and oscillating back upward. This motion has continued for billions of years and will continue until the galaxy itself transforms through merger or other evolution. The Milky Way contains stellar nurseries active right now. Regions like the Orion Nebula, the Eagle Nebula, the Carina Nebula are forming stars as you rest. Protostars collapsing from gas clouds, planetary disks forming around them, perhaps planets coalescing that will someday host life, intelligence, civilizations wondering about their own origins. Star formation is inefficient. Only about 1% of a molecular cloud's mass typically ends up in stars. The rest is blown away by stellar winds and supernova explosions before it can collapse. Most of the gas returns to the interstellar medium, available for future star formation, recycled through multiple generations. Each star formation region is unique, different sizes, different triggering mechanisms, different stellar populations. Some form mostly Loma stars. Others produce a few massive stars that dominate the region's evolution. Some are isolated. Others are part of larger complexes. Diversity is the norm. No two nurseries are identical. These regions are beautiful when photographed. Long exposure images reveal glowing gas colored by emission from different elements: hydrogen producing red, oxygen producing green and blue, creating false color images of stunning complexity. The photos show what eyes cannot: the faint glow amplified, colors separated, structure revealed that visual observation cannot capture. You're looking at ongoing creation when you observe these nebulae. Stars being born, planets forming, systems assembling themselves from chaos through gravity's patient action. It's creation happening now, not ancient history, but contemporary process. The galaxy perpetually renewing itself, maintaining star population through continuous formation. The Sun completes one orbit every 225 to 250 million years. This period, called a cosmic year or galactic year or galactic years, the fundamental timescale for solar motion through the galaxy. Everything tied to orbital position encounters with spiral arms, passages through the disk midplane, variations in cosmic environment operates on this timescale. Since forming, the Sun has completed 18 to 20 galactic orbits. That's 18 to 20 trips around the galaxy, 18 to 20 encounters with each major spiral arm, 18 to 20 complete circuits through varying galactic environments. Each orbit brings new surroundings, different stellar neighbors, changing conditions, though the variations are subtle over single orbit. During each orbit, the solar system encounters different stars. The stellar neighborhood constantly changes, stars overtaking us from behind, stars being overtaken, new neighbors appearing while old ones recede. The stars visible from Earth today are different from those visible a galactic year ago and different from those that will be visible a galactic year hence. Some stars move faster, some slower. O and B stars, young, massive, blue, often remain near their birth locations in spiral arms because they live only millions of years. Older stars have time to migrate far from formation sites, mixing throughout the disk. The oldest stars have circled the galaxy dozens of times, their birth locations no longer discernible. You're on a cosmic merry-go-round, endlessly circling, returning repeatedly to similar positions, yet never quite to the same place because the galaxy evolves. Spiral arms move, the environment changes. Each orbit is unique, despite traveling the same path, different each time. Familiar yet novel, predictable yet surprising. The Milky Way's spiral pattern is temporary. The exact configuration of spiral arms changes over hundreds of millions of years as the density wave rotates and evolves. As gas flows respond to gravitational perturbations, as star formation proceeds and fails, the spiral pattern you see now differs from what existed a billion years ago and from what will exist a billion years hence. Spiral structure might even come and go. Some galaxies show transient spiral patterns that persist for some time, then fade, possibly replaced by new patterns. The Milky Way's spiral might not be a permanent feature, but temporary organization, destined to change or disappear as galactic dynamics evolve. The bar's presence affects spiral structure, stability. Barred spirals' arms typically begin at the bar's ends, making the spiral pattern dependent on the bar's properties. If the bar evolves or dissolves, the spiral structure would change accordingly. Bar and spiral are coupled features, neither independent of the other. Future observations might reveal spiral evolution by precisely mapping the Milky Way's structure now and comparing to past observations. Astronomers might detect changes in spiral arm positions or shapes occurring over decades, extremely rapid by galactic standards, but potentially detectable with sufficiently precise measurements. You live in a dynamic, evolving galaxy, not a static, unchanging structure, but a living system, continuously rearranging, perpetually adjusting, constantly responding to internal dynamics and external perturbations. The stability you perceive is relative in million-year timescales. Everything changes, yet on human timescales, everything seems eternal. Let your thoughts spiral like galactic arms, graceful curves winding through mental space, patterns emerging and dissolving, structures temporary yet beautiful, organization arising from chaos, meaning created through relation, all of it flowing, changing, eternal yet ephemeral. The Milky Way is one of billions of galaxies in the observable universe. Our home is not unique or central, but one among multitudes, a single island in a vast cosmic ocean. This multiplicity is humbling. We're part of something immensely larger. One small structure in a universe of structures, significant locally, but typical cosmically. Yet, the Milky Way is our home, the only galaxy we'll ever truly know, the only one we inhabit, the one galaxy from which we experience the universe. Its particulars, its mass, structure, composition determine our existence, providing the environment that enables Earth, life, consciousness, wondering about place in cosmos. This combination, cosmic typicality and personal significance, captures a deep truth. You're both insignificant and central, typical and unique, one among many, yet the only you. The Milky Way embodies this paradox at galactic scale, ordinary among galaxies, essential to those within it. The galaxy contains your entire history. Every human who ever lived, every civilization that ever rose, every thought ever thoughtful occurred within this one galaxy, within one small region, near one ordinary star, orbiting in the galactic suburbs. All of human experience, compressed into a point in space, barely distinguishable at galactic scales. Yet this point is where meaning lives. Galactic scales are impressive but impersonal. Human scales, where love and loss happen, where joy and sorrow arise, where consciousness experiences existence. These scales are where the universe becomes aware of itself, where matter contemplates matter, where the cosmos observes cosmos. The Milky Way's disk is warped and rippled beyond the overall warp mentioned earlier. The disk shows smaller scale distortions, ripples, like waves on a pond. possibly caused by satellite galaxy passages or by dark matter substructure moving through the disk, creating gravitational disturbances that manifest as vertical waves in stellar distribution. These ripples might correlate with mass extinction events on Earth. Some scientists speculate that disk passages, when the solar system crosses the galactic midplane, might disturb the Oort cloud, sending comets toward the inner solar system, increasing impact rates on Earth. The correlation is weak and controversial, but it's a reminder that galactic environment might affect terrestrial life. The most recent passage through the midplane occurred about 3 million years ago. If there are effects from disk crossings, they might be unfolding now. Though on timescales of millions of years, too slow for humans to perceive, too long for civilizations to track, yet potentially significant on evolutionary timescales. These effects, if real, are subtle. The galaxy doesn't threaten Earth directly. We're too far from the center, too far from massive stars, protected by the Sun's heliosphere and Earth's magnetic field. But indirect effects through comet showers or cosmic ray variations might exist. Galactic environment influencing terrestrial evolution in ways we're only beginning to explore. You're safe despite cosmic context. The universe contains violent processes, supernova, black holes, galaxy collisions, but at your location, at this time, conditions are benign. The galaxy provides stable environment. The Sun orbits in relatively peaceful region. Earth is protected by multiple layers of defense. Cosmic violence exists, but rarely reaches here. The Milky Way looks different from different angles. From Earth embedded in the disk, we see a band stretching across the sky. From above or below, hypothetical observers would see beautiful spiral structure spread out like cosmic flower. From edge-on, perpendicular to Earth's view, they'd see a thin line, the disk's extreme flatness, making the galaxy nearly disappear in profile. No one will ever see these other views. We're stuck inside, our perspective forever limited to views from within. Maps showing the Milky Way from outside are reconstructions, educated guesses based on measurements from inside, extrapolations assuming our galaxy resembles other spirals we can see from outside. This limitation mirrors human condition. We experience reality from one perspective, embedded within the system we're trying to understand, never able to step outside and see the whole from an external viewpoint. All knowledge is perspectival, limited by viewpoint, constrained by position. Yet we can know much despite limitations. Through careful observation, clever inference, mathematical modeling, we can reconstruct the whole from partial views, understand structure despite being embedded within it, map the galaxy despite never leaving it. Intelligence enables transcending immediate perspective through thought. You're both trapped and free. Trapped in position, unable to leave the galaxy or see it from outside, forever bound by perspective. Yet free in mind, able to imagine other views, reconstruct the whole, understand structure intellectually despite being embedded physically. This is consciousness's gift, transcending immediate experience through imagination and reason. As sleep approaches deeper, let galactic perspective provide comfort. Your concerns are real but local, significant at human scales but negligible cosmically. The galaxy knows nothing of your worries, continues regardless of your thoughts, exists independently of your consciousness. This independence is liberating. The cosmos doesn't require your attention, doesn't demand your management, simply is allowing you to rest, releasing you from responsibility, permitting peaceful sleep. The Milky Way's light takes 100,000 years to cross from one edge to the other. Even traveling at the universe's ultimate speed, limit light speed, 300,000 kilometers per second, departing one side of the galaxy wouldn't reach the other side for 100 millennia. This is the galaxy's true scale, measured not in kilometers, but in the time light requires to traverse it. During that crossing time, human civilizations could rise and fall multiple times. All of recorded history about 5,000 years fits into that journey 20 times over. The light that left the far side of the galaxy when humans were living in Stone Age conditions is only halfway across now. Won't reach our side until long after our civilization has transformed beyond recognition or disappeared entirely. This light carries information about distant regions. Every photon arriving from the galactic edge was emitted thousands of years ago, carrying news of conditions when it departed. We see the galaxy not as it is now, but as it was, different parts at different times. A composite image where simultaneity has no meaning. The galaxy's diameter in light years reveals its vastness more clearly than kilometers ever could. Numbers like 100,000 light years or 1 quintillion kilometers are equally incomprehensible. But light years connect to time, making the distance somehow more tangibly. You're seeing the galaxy's past whenever you look at it. The Milky Way band stretching across the night sky shows you thousands of years of history simultaneously. Near stars as they were years ago, distant stars as they were millennia ago, all collapsed into single view that appears simultaneous but represents different times. The Milky Way has a metallicity gradient with age. The oldest stars, regardless of location, have low metallicity. They formed when the galaxy was metal poor. Younger stars show position-dependent metallicity, high near the center, where enrichment proceeded quickly, lower in outer regions, where stellar generations turned over more slowly. Age and position together determine stellar composition. This creates a fossil record in stellar populations. By measuring a star's metallicity and age, astronomers can infer where and when it formed, tracing how stars migrated through the galaxy over time. Some old metal-poor stars now in the disk might have formed in dwarf galaxies, later consumed by the Milky Way migrants from destroyed systems. Refugees incorporated into our galaxy. Chemical evolution is complex and ongoing. Each supernova adds new elements to the interstellar medium. But the mix isn't uniform. Massive stars produce different element ratios than smaller stars. Supernova types vary in their yields. Mixing is incomplete, creating chemical heterogeneity that persists across the galaxy. The sun's composition reveals its history. By analyzing sunlight spectrally, astronomers determine the sun contains every naturally occurring element, mixed in proportions, reflecting the gas cloud's composition 4.6 billion years ago. That composition, in turn, reflects billions of years of stellar nucleosynthesis in the solar neighborhood. You're made of this chemical heritage. Every element in your body was created somewhere. Sometime hydrogen in the Big Bang, carbon in stellar cores, iron in supernova explosions, gold in neutron star mergers. Your body is a museum of nucleosynthesis, collection of elements with histories spanning cosmic time, assembled briefly into form capable of consciousness. The galactic center hosts extraordinary stellar orbits. Stars near Sagittarius A** move at up to 7,000 kilometers per second, 2% of light speed, completing orbits in as little as a few years despite traveling paths that span light days. These are the fastest stellar orbits known, enabled by the central black hole's intense gravitational field. One star, called S2 or SO22, orbits the black hole every 16 years. Its elliptical orbit brings it within 17 light-hours of the black hole, closer than Saturn is to the Sun, where it experiences extreme gravitational effects, including significant time dilation and orbital precession. Monitoring this star tests general relativity in the strong field regime, impossible to access elsewhere. These orbits prove the black hole exists. Only an extremely compact, massive object could make stars move so fast in such small regions. The orbital data constrains Sagittarius A** mass to about 4 million solar masses and its size to less than the orbit of Mercury, essentially proving it's a supermassive black hole rather than some exotic alternative. Watching these stars move requires patience and precision. Observations spanning decades track positions to within microarcseconds angles, so small they're like measuring the width of a human hair from 5,000 kilometers away. This precision, combined with long baselines, allows astronomers to reconstruct orbital paths and determine the central mass. You orbit at a sedate pace by comparison. The Sun's 230 km per second orbital velocity is slow compared to these inner stars' thousands of kilometers per second. You're in the galactic suburbs where gravity is gentler, orbits are larger and slower, conditions are calmer, making this region hospitable for long-term stability and life. The Milky Way's rotation curve has been measured out to 50,000 light-years. Beyond that distance, observations become difficult. Stars are sparse, gas clouds rare, measurement uncertainties large. But within that radius, the rotation curve is well determined, showing the characteristic flat behavior that indicates dark matter dominates the mass. Extending measurements to larger distances is active research. New surveys identify tracer objects in the outer galaxy, distant stars, stellar streams, satellite galaxies whose velocities constrain the rotation curve at large radii. Each extension provides better constraints on dark matter distribution, improving models of the galaxy's mass profile. The rotation curve might eventually decline at very large radii. If the dark matter halo has finite extent, orbital velocities should decrease beyond its edge, following normal Keplerian behavior, where velocity decreases with distance. But if the halo extends indefinitely, or at least two distances we cannot observe, the curve might stay flat, essentially forever. This uncertainty about the outer galaxy reflects observational limits. We can see only so far, measure only so precisely, detect only objects bright enough to observe. The Milky Way's structure in its outermost regions remains uncertain, known only roughly, awaiting future observations to clarify. You orbit in the well-explored region. The solar neighborhood within a few thousand light-years is mapped in great detail, every bright star catalogued, motions measured precisely. You live in the known territory, the surveyed region, where galactic structure is understood clearly, if not completely. The Milky Way produces about 3 supernovae per century. These stellar explosions, occurring when massive stars exhaust their fuel or white dwarfs, accumulate too much mass, release as much energy in a few weeks as the Sun will emit over its entire lifetime. They're rare, only a few per century across the entire galaxy, but each one significantly affects its surrounding. The most recent observed supernova in the Milky Way occurred in 1604, called Kepler's supernova. It was visible to the naked eye, bright enough to see in daylight, studied by Johannes Kepler and other astronomers of the era. Since then, over 4 centuries have passed without another visible supernova in our galaxy, an unusually long gap, purely by chance. Other supernovae have occurred, but were hidden by dust. Observations in infrared and radio wavelengths have identified supernova remnants from explosions in the past few centuries that went unnoticed optically because intervening dust blocked the light. The galaxy has been more active than visible observations suggest. The next nearby supernova is unpredictable. Betelgeuse in Orion is often mentioned as a Candidata red supergiant, star that could explode any time from today to 100,000 years hence. When it does explode, it will be spectacular bright as the full moon, visible during daytime, casting shadows at night, dominating the sky for weeks. But predicting exactly when is impossible with current understanding. You're unlikely to witness a nearby supernova. They're rare, and you're mortal, and the odds are against it. But the possibility exists, perhaps in your lifetime, perhaps in your children's lifetimes. A star will explode close enough to see clearly, providing humanity with direct observation of one of the universe's most energetic events.
Tonight, we're going on a journey,
violence
not to distant galaxies or alien worlds,
spectacle.
but
the Milky Way's magnetic field strength is about 6 microgauss. That's 6 millionths of a Gauss, about 10,000 times weaker than Earth's magnetic field at the surface, incredibly feeble by terrestrial standards. Yet integrated over the galaxy's vast volume, this weak field contains enormous total energy, affects charged particle motions, organizes the interstellar medium's structure. This field is measured through its effects on radio waves. Pulsars emit polarized radio pulses that rotate as they propagate through magnetized plasma. The amount of rotation depending on the magnetic field strength along the line of sight by measuring rotation from many pulsars in different directions. Astronomers reconstruct the galactic magnetic field structure. The field follows a spiral pattern in the disk. In some regions, it aligns with spiral arms. In others, it winds between them. The field's geometry is complex, not perfectly regular, showing turbulence and reversals, reflecting the chaotic processes that generate and maintain its supernova explosions, stellar winds, gas flows, all contributing to the field's structure. Magnetic fields are hard to study observationally. They don't emit light, don't absorb light, affect only charged particles and polarized radiation. Understanding galactic magnetic fields requires indirect methods, careful observations of subtle effects, theoretical modeling to interpret measurements. It's detective work, reconstructing invisible structure from limited clues. You're bathed in this weak field constantly. It passes through you without effect, too weak to influence biological processes, undetectable by any sense. Yet it shapes your cosmic environment, affects the charged particles that create space weather, plays a role in protecting the solar system from some galactic cosmic rays. The Milky Way's star formation rate has declined over time. The galaxy formed stars most vigorously billions of years ago when gas was abundant and conditions favorable. Since then, the rate has gradually decreased as gas is consumed and locked into stars and stellar remnants. Feedback from supernova and stellar winds makes star formation less efficient. The galaxy slowly exhausts its star-forming material. Currently, the Milky Way forms about 3 solar masses of new stars per year. This seems like a lot equivalent to 3 suns forming annually, but spread across the galaxy's vast volume, it's actually modest. Most of the galaxy experiences no star formation currently. Active nurseries are confined to specific regions, mostly in spiral arms where gas concentrates. This rate is low compared to starburst galaxies. Some galaxies experiencing mergers or other disturbances form hundreds or thousands of solar masses per star, formation rates that would exhaust the Milky Way's gas reserves in tens of millions of years. Our galaxy forms stars at a sustainable rate, likely to continue at similar levels for billions of years. Eventually, star formation will cease entirely, as gas is consumed and not replaced, as the interstellar medium is gradually depleted. Star formation will slow, then stop, the galaxy becoming red and dead, containing only aging stars. No new formation, slowly fading as old stars exhaust their fuel. You live during the galaxy's mature phase. Star formation continues, but at reduced rates. The galaxy past its youth, but not yet elderly, creating new stars steadily, if not vigorously. This timing is fortunate, too early, and the galaxy would be chaotic and dangerous. Too late, and conditions might not support life as readily. The Milky Way contains approximately 10,000 open star clusters. These loose associations of young stars, typically containing dozens to thousands of members, form from molecular clouds and gradually disperse over tens to hundreds of millions of years as stellar encounters and galactic tidal forces pulled them apart. Their temporary structures, stellar siblings that drift apart as they age. The Pleiades is a famous example, visible to the naked eye. About 100 million years old, this cluster in Taurus contains several hundred stars, the brightest of which form the distinctive pattern visible without optical aid. The cluster is still compact. Stars are separated by only a few light years, but is gradually dispersing, destined to disappear as a recognizable group within a few 100 million years. These clusters are laboratories for stellar evolution. Because member stars all formed together from the same cloud, they have the same age and initial composition. Differences between members reflect only mass differences, allowing astronomers to test stellar evolution theory by comparing stars of different masses at the same age. Most clusters don't survive long. Galactic tidal forces and close encounters with molecular clouds gradually strip away members, dispersing the cluster into the general stellar population. Only the most massive or most isolated clusters survive for billions of years. Most dissolve within a few 100 million years of formation. The Sun probably formed in such a cluster. Its birth cluster, perhaps containing thousands of stars, has long since dispersed. Members now scattered across the galaxy, moving on independent orbits, no longer recognizable as a coherent group. Your stellar siblings exist, but are lost among billions of other stars, indistinguishable without detailed analysis. The galactic bulge is shaped like a peanut. Viewed edge-on, the bulge appears to have 2 lobes above and below the plane, creating a boxy or peanut-like shape. This structure results from the bar's presence. The bar extends vertically as well as horizontally, creating the distinctive shape visible in edge-on views of barred spirals like ours. This shape reveals the bar's orientation. The peanut structure tells us the bar is tilted relative to our line of sight. Viewed at an angle, rather than face-on or egon. Combined with other observations, this constrains the bar's angle to about 25 to 30 degrees from the Sun galactic center line. Infrared observations best reveal this structure. At optical wavelengths, dust obscures the view. At infrared wavelengths, dust becomes transparent, allowing clear views of the bulge's shape. Surveys like 2MASS and WISE have mapped the bulge in detail, revealing its complex three-dimensional structure. Understanding the bulge's shape helps constrain galactic dynamics. The bulge's structure depends on how the bar formed and evolved, what forces shaped it, how it exchanges energy and angular momentum with the surrounding disk. Matching observations to simulations helps test theories of galactic evolution. You orbit around this complex central structure, not a simple spherical bulge, but a dynamically active bar extending vertically and horizontally, rotating, evolving, shaping gas flows and stellar orbits throughout the inner galaxy. The core you orbit around is more complex than simple models suggest. The Milky Way's thin disk is about 300 light-years thick at the Sun's location. This is the stellar disk's most prominent component, containing young stars, gas, active star formation, the galaxy's most dynamically active region. It's remarkably thin if you scaled the galaxy down to the size of a CD. The thin disk would be thinner than the CD's plastic, more like a film coating its surface. Most star formation occurs in this thin disk. Gas concentrates here due to dissipative collisions that remove random vertical motions, settling matter into the narrowest possible plane. This concentration makes conditions favorable for star formation. Densities are higher, collisions more frequent, gravitational collapse more likely. Young stars remain in the thin disk. They haven't had time to be scattered into thicker distributions by gravitational encounters with molecular clouds or spiral arms. As stars age, random kicks gradually increase their vertical velocities, causing them to explore regions farther from the midplane, thickening their distribution. The Sun orbits within this thin disk. We're currently about 65 light-years above the midplane, well within the thin disk's 150 light-year half-thickness, moving downward toward the midplane, which will cross in a few million years before continuing downward, then reversing and oscillating back upward. You're embedded in the galaxy's most active region. The thin disk is where things happen: star formation, supernova, molecular cloud complexes, massive young stars. It's the galactic engine room where fresh stars are made and old ones die, where matter cycles through stellar generations, where the galaxy renews itself. The Milky Way's thick disk contains older stars, with a scale height of about 1,000 light-years, 3 times thicker than the thin disked component. Consists of stars, typically several billion years old, formed earlier in the galaxy's history, gradually heated to higher vertical velocities by gravitational perturbations over their lifetimes. The thick disk has different chemistry than the thin disk. Its stars show lower average metallicity and different abundance patterns, suggesting they formed under different conditions or in different locations. Some thick disk stars might have formed in the outer galaxy and migrated inward. Others might have formed early when the galaxy was still settling into its current configuration. How the thick disk formed is debated. It might be dynamically heated, thin disk stars, born in the plane, then kicked to higher velocities by past disturbances. Or it might be a separate population, formed early through different processes, coexisting with but distinct from the thin disk formed later. The boundary between thin and thick disks is gradual, not sharp. There's no clear dividing line, just a gradual transition where the population of young metal-rich stars decreases and the population of older metal-poor stars increases. Nature doesn't respect our categories. The division between thin and thick is human construct imposed on continuous distribution. You're near the boundary region. At 65 light-years above the midplane, the Sun is in the thin disk but approaching the thick disk's domain, sampling both populations, experiencing the transition between the galaxy's most and moderately active regions. The Milky Way's stellar halo extends far beyond the visible disk. While the disk ends at about 50,000 light-years, the halo continues to perhaps 200,000 light-years or more, gradually fading into the intergalactic medium. This enormous sphere of old stars, globular clusters, and dark matter surrounds the disk like fog around a streetlight. The halo contains less than 1% of the galaxy's stars. Despite its enormous volume, the halo is extremely sparse. Stellar densities are thousands or millions of times lower than in the disk. Most halo volume is essentially empty, containing only rare, scattered stars on lonely orbits through the galactic outskirts. Halo stars move on highly elliptical orbits, unlike disk stars circling neatly in the plane. Halo stars plunge through the disk, then soar far above it, their orbits oriented randomly, creating a non-rotating spherical distribution. They're cosmic wanderers, not participating in orderly galactic rotation, but following individual trajectories. Some halo stars are passing through your neighborhood right now. High-velocity stars, moving through the solar vicinity at unusual angles relative to the disk, are often halo members, temporarily passing through the disk on their elliptical orbits. They're strangers passing through, not local residents, visitors from the outer galaxy. You're surrounded by the inner halo, even though you orbit in the disk. The halo's inner regions overlap with the disk's outer regions, the two populations coexisting. Stars from both populations occupying the same volume, but moving differently, like two crowds walking through each other in opposite directions. The Milky Way will collide with Andromeda in about 4.5 billion years. This future merger, already set in motion, already inevitable, will transform both galaxies, destroying their spiral structures, creating a single elliptical galaxy from the wreckage. It's the next major event in the Milky Way's history, coming collision that will end the galaxy as we know it. The merger will take several billion years to complete. The galaxies will approach, pass through each other, separate again, then fall back together in a cosmic dance spanning billions of years. With each passage, tidal forces will distort structures, trigger star formation, redistribute matter, gradually merging the two systems. Individual stars will rarely collide. Despite billions of stars in each galaxy, the vast spaces between them mean stellar collisions will be extremely rare. Most stars will pass through the merger unscathed, their orbits redirected but their physical integrity maintained, evidence that space is mostly empty even within galaxies. The resulting galaxy is sometimes called Milky. This portmanteau combining Milky Way and Andromeda names the merger product, the elliptical galaxy that will exist 5 or 6 billion years from now, containing all stars from both current spirals, organized in new configuration without spiral structure or active star formation. You won't experience this merger. It's too far in the future. The the Sun will have entered its red giant phase by then. Earth likely rendered uninhabitable by the aging Sun's increasing luminosity. The merger will occur, but not in the presence of Earth as we know it, not witnessed by humanity as we exist now. Let your breathing match the slow cosmic rhythms, the patient merger across billions of years, the gradual evolution of galaxies, the unhurried dance of gravitationally bound systems approaching through the dark. All proceeding without rush, without urgency, cosmic patience exemplified. The Milky Way's dark matter halo is probably spherical or slightly flattened. Models and observations suggest the halo's shape is nearly round, not disc-like or strongly elongated, though exact shape remains uncertain. This spherical distribution reflects dark matter's collisionless nature. It doesn't dissipate energy through collisions, so doesn't settle into a disk like normal matter does. The halo's mass profile determines orbital velocities. Stars and gas orbit within the gravitational potential created by all mass stars, gas, dark matter combined. By measuring orbital velocities at different distances and using gravitational theory, astronomers can infer the dark matter distribution, determining how density varies with radius. Different dark matter profiles make different predictions. NFW profiles, named after Navarro, Frank, and white product density increasing toward the center following specific mathematical form. Other profiles predict different behaviors. Comparing predictions to observations constrains which profiles match reality, helping determine dark matter's properties. The halo probably extends to several 100,000 light-years. Beyond that distance, the Milky Way's gravitational influence weakens, shading into the gravitational fields of other local group galaxies. The halo's edge is not sharp but gradual, a fade-out rather than a boundary. Regions where multiple galaxies' halos overlap and interact. You're deep within this dark matter halo, at the Sun's position, a few hundred times less dense than the stellar disk, but still significant. You orbit through invisible substance, surrounded by dark matter, experiencing its gravitational effects, even though it remains undetectable, except through those effects. The Milky Way's formation involved both top-down and bottom-up processes. Top-down formation large structures, fragmenting into smaller ones, and bottom-up formation small structures, merging into larger ones, both contributed to the galaxy's assembly. The halo likely formed early through multiple mergers. The disk formed later as gas settled and star formation proceeded. This mixed history explains the galaxy's structure. The spherical halo, with chaotic orbits, reflects violent early history mergers and accretions, creating scrambled stellar populations. The ordered disk reflects later evolution gas, settling through dissipation, forming stars in organized way, creating the rotating thin disk observed today. Evidence for this history appears in stellar populations. Old metal-poor halo stars show properties consistent with early formation in small systems later merged. Younger disk stars show properties indicating formation from gas enriched by previous stellar generations, assembled in more orderly fashion. The galaxy is still forming in some sense. It continues accreting satellites, adding mass, growing slowly. It hasn't reached final equilibrium. It's still evolving, still changing, still incorporating new material. The Milky Way you see now is not the Milky Way's final form, but a snapshot of ongoing evolution. You inhabit a galaxy with complex history and uncertain future, formed through mergers, shaped by accretions, destined for more mergers. The Milky Way is dynamic system, not static structure. Nothing is permanent. Everything evolves. Change is the only constant. The Milky Way's outer regions are poorly understood. Beyond about 50,000 light-years from the center, observations become sparse. Stars are rare. Gas is thin. Measurements are difficult. This outer galaxy containing perhaps 10% of the total stellar mass remains incompletely mapped. Its structure, known only roughly. New surveys are improving this situation. Projects like Gaia and SDSS are discovering faint stars and structures in the outer galaxy, gradually mapping regions previously unknown. Each discovery adds detail to the picture, filling in gaps, revealing structures, stellar streams, dwarf galaxies, extended stellar populations that were invisible before. The outermost reaches blend into the local group at several 100,000 light-years from the galactic center. The Milky Way's halo merges with Andromeda's halo, to galaxies' dark matter overlapping, gravitational fields interacting. The boundary is fuzzy, a transition rather than a hard edge. This outer region contains clues to the galaxy's history. Stellar streams from disrupted satellites, chemical patterns revealing ancient enrichment, kinematics showing past merger events, all preserved in the outer galaxy's sparse stellar populations, waiting to be discovered and interpreted. You're well within the known region. The solar neighborhood is thoroughly studied. Every bright star cataloged, structure well understood. You orbit in explored territory, the well-mapped regions, where the Milky Way's nature is clear, even if not complete. The Milky Way produces stellar winds totaling billions of tons per second. Every star emits wind streams of charged particles flowing outward from stellar surfaces, the sun's solar wind being just one example. Summed across hundreds of billions of stars, these winds contain enormous mass flux, filling the interstellar medium with material shed from stellar atmospheres. These winds affect the interstellar medium. They heat gas, create bubbles and cavities, drive turbulence, affect star formation. Massive stars' winds are particularly powerful, clearing regions around them, creating stellar wind bubbles that persist for millions of years after the stars explode as supernova. The winds carry mass away from stars. The sun loses about 1 million tons per second to its solar wind, teeny compared to the sun's total mass, but significant over billions of years. More massive stars lose mass faster, shedding substantial fractions of their mass over their lifetimes, enriching space with material from stellar interiors. These winds eventually become part of future stars. The material shed by current stellar generations mixes into the interstellar medium, becomes incorporated into molecular clouds, collapses into new stars. It's cosmic recycling stars, shedding material that becomes raw material for future stellar generations. You're breathing the products of ancient stellar winds. The oxygen in your lungs was created in massive stars billions of years ago, expelled in stellar winds or supernova explosions, incorporated into the molecular cloud that formed the sun and planets. Later released by geological processes, now part of Earth's atmosphere, temporarily passing through your body before being exhaled and continuing its journey through the cosmic cycle. As deeper sleep approaches, let galactic timescales soothe your mind. Billions of years for galaxy formation, hundreds of millions for stellar orbits, millions for stellar lifetimes, all stretching far beyond human perception. placing your momentary concerns in perspective, showing them as brief fluctuations in longer processes, temporary states in ongoing evolution. The galaxy continues without your attention, following physical laws, evolving through gravitational interactions, maintaining structure through balance of forces, all proceeding independently, requiring nothing from you, allowing you to rest peacefully, knowing the cosmos takes care of itself. You're seeing one moment in the galaxy's continuous evolution. The spiral structure, visible on dark nights, is current configuration, temporary arrangement that will change over time, snapshot of ongoing process rather than permanent state. Change is the constant. Stability is relative. Everything flows. Let these thoughts of cosmic change and flow carry you deeper into rest. Nothing is permanent. Everything transforms. Structures arise and dissolve. Patterns form and fade. All of it natural, all of it inevitable. The universe's way, change the only constant. The Milky Way has taught humanity humility. When we thought Earth was the universe's center, we were wrong. When we thought the solar system was unique, we were wrong. When we thought the Milky Way was the entire universe, we were wrong. Each discovery expanded our horizons, showed us as smaller and less central, taught us our place in vast cosmos. Yet this humility is empowering rather than diminishing. Understanding our smallness, our typicality, our cosmic ordinariness doesn't diminish our significance, it contextualizes it. Participants in cosmic story spanning billions of years and billions of light years. The galaxy contains you, but doesn't define you. You're part of it, embedded within it, shaped by it, dependent on it, yet also distinct from it. Possessing consciousness it lacks, capable of understanding it doesn't have, experiencing subjectivity it cannot know. You're part of the galaxy and separate from it simultaneously, both contained and transcendent. This paradox, being part of while also observing, embedded within while also separate from, characterizes conscious existence. You're the galaxy observing itself, the cosmos become aware of cosmos, matter contemplating matter, the universe's way of knowing itself through localized self-awareness. You're cosmically ordinary, yet individually unique, made of common elements, embedded in typical location, in an average galaxy, yet uniquely you, possessing experiences no one else has, consciousness that exists only once and never again. Ordinariness and uniqueness coexist, both true simultaneously. As our journey through the Milky Way comes to its gentle close, let's reflect on what these 100 facts have shown us. Not just information about stellar populations, dark matter distributions, or galactic dynamics, but deeper truths about existence, about our place in the cosmos, about the nature of wonder itself. The galaxy has revealed its vastness, 100,000 light years across, containing hundreds of billions of stars, masses beyond comprehension, timescales exceeding imagination. Yet, within that vastness, you exist, one conscious being on one planet. The scale is humbling, the improbability staggering. Yet, here you are, aware and wondering. The galaxy has shown its beauty's spiral arms, traced in light, nebulae glowing with stellar birth, streams of destroyed satellites, mapping past violence, structures of exquisite complexity. This beauty exists whether humans observe it or not. Patterns unfolding according to physical law, magnificence without audience, splendor without purpose beyond itself. the galaxy has demonstrated its aged 13.6 billion years of history, countless stellar generations, ongoing evolution from chaotic youth to structured maturity. Human history occupies the tiniest sliver of this time span, civilization a microsecond in the galactic day. Yet consciousness arose in this brief moment, allowing the galaxy to know itself, however briefly. The galaxy has taught connection you're made from its substance, shaped by its history, embedded in its structure. The atoms in your body were forged in its stars, cycled through its medium, incorporated into your temporary form. You're not separate from the galaxy, but part of it, consciousness arising from matter, awareness emerging from cosmos. The galaxy has preserved mystery dark matter undetected, formation history incompletely known, future uncertain, countless questions unanswered. Despite centuries of study and decades of sophisticated observation, the Milky Way keeps secrets, reveals truths gradually, reminds us that understanding is always incomplete, knowledge always partial. These lessons, humility without diminishment, beauty without purpose, connection through substance, mystery despite knowledge are gifts the galaxy offers to those who contemplate it. Not practical gifts, not useful in daily life, but gifts of perspective, context, wonder, meaning. These matter too, perhaps more than practical concerns. Tonight, you've traveled through your cosmic home, from the central black hole to the outer halo, from ancient globular clusters to active star-forming regions, from dark matter halos to spiral arms traced in starlight. You visited every region, learned every major feature, understood the structure that contains everything humanity has ever known. The galaxy continues orbiting, stars continue burning, gas continues cycling through stellar generations. All of this proceeds, whether you attend to it or not, whether you understand it or not, whether you exist or not. The cosmos is independent, self-sufficient, requiring nothing from consciousness, yet somehow producing consciousness, creating awareness without apparent purpose. This independence is comforting. The galaxy doesn't need your attention, doesn't require your understanding, simply is. You can rest peacefully, knowing the cosmos continues, structures persist, beauty endures without your effort or concern. The universe takes care of itself, allowing you to rest. As sleep approaches, let the galaxy's immensity cradle you. You're held by gravity that extends across 100,000 light-years, participating in motions that span hundreds of millions of years, composed of elements created over billions of years. You're part of ancient, vast, continuing process brief, eddy in long flow, temporary pattern in eternal substance. The Milky Way has been your home tonight, your guide through cosmic spaces, your companion on this journey through stellar cities and dark matter seas. It will remain your home tomorrow, next year, throughout your life, containing everything you'll ever directly experience, providing the stage on which your life unfolds. Thank you for traveling through the galaxy tonight, for bringing curiosity and wonder to this journey, for allowing these cosmic facts to carry you toward sleep. The Milky Way spins on, patient and eternal, its stars shining whether observed or not, its beauty existing whether appreciated or not, its mysteries waiting whether explored or not. Rest now in your cosmic home. You're safe in the galactic suburbs, orbiting peacefully, held by gravity, surrounded by stars, embedded in structure, older than Earth, vaster than comprehension, more beautiful than words capture. The galaxy embraces you, not actively or consciously, but through the simple fact of your existence within it, your participation in its vast structures, your temporary residence in its ancient spaces. Let the darkness between the stars fill your mind, peaceful, cool, quiet darkness, space so vast that even traveling at light speed takes millennia to cross. Let that spaciousness enter your thoughts, creating room for rest, space for sleep, emptiness for peace to fill. The Milky Way continues its eternal rotation, stars following their appointed paths, gas cycling through stellar generations, dark matter holding everything together through invisible gravity. All of it proceeds without effort, without struggle, without resistance. Cosmic example of effortless being, perfect doing through not doing, existence through simple presence. Be like the galaxy, tonight simply be, without effort or intention, present without striving, existing without struggling. Let consciousness fade like starlight into distance, thoughts dissolving like nebulae into darkness, awareness becoming peaceful as deep space, quiet as vacuum, still as the vast galactic pauses between starbirths. The Milky Way holds you gently as you drift toward sleep. You're part of it, embedded within it, forever bound to it by gravity and history and substance. It's your home, your origin, your context, the structure that gives meaning to your existence by showing where and when and how you fit into the cosmic story. Sleep peacefully, galactic traveler. Rest well, conscious being. Dream gently, stardust child. The Milky Way watches over you, not consciously or deliberately, but through simple fact of your existence within its protective embrace. Spinning slowly through space, carrying you and all you know through the cosmic dark. Good night.